Last time, in probability and measure, we proved the strong law of large numbers. It shows how the sum of a bunch of independent random variables divided by the sample size, n, tends to the mean, the long-run average, almost surely. But there's many different ways that a sum can converge, or a sum of random variables can converge. If we were to change by dividing by n to divide by the square root of n, we get convergence in distribution. That is, we have weak convergence of measure when we think of these as probability measures, and suddenly the entire behavior of the system changes. This is the central limit theorem and is the main topic of today's lecture. In the central limit theorem, what we're doing is we are scaling our sum by the square root of the sample size, and what will happen is it will converge in distribution, but it doesn't converge to just any distribution, it converges to the Gaussian distribution. And it reminds us that you are normal, I'm normal, we're all normal, according to the central limit theorem. That is, at least in the long-run average. So how are we going to go about trying to prove the central limit theorem? Well, we're going to need a lot more tools. We need characteristic functions, which are really just Fourier transforms. And we need to use the Prohorov theorem, which is a type of compactness result for probability measures. It's going to be a really good time. So let's go back and get into those notes. Welcome back to another lecture of probability and measure. Last time we talked about the strong law of large numbers, one of the critical pieces of probability theory and statistics. Today we're going to talk about the other extremely significant piece of probability theory and statistics, and that is the central limit theorem. The idea that, well, if I sum up a bunch of things and normalize it in just the right way, I'm going to get something that's, well, normal, or a Gaussian distribution. Now, why is this true? I mean, it's kind of something that we see all over the place, right? We see the bell curve showing up everywhere in nature, and it's quite fascinating that it should. And in fact, we can prove a mathematical theorem that says, yes, this actually is the case, that in the limit, things become, well, normal or Gaussian. To get there, we need to do a little bit of work. We need to talk about, well, how do measures converge? We need to do this a little bit more precisely. We need to consider specifically the characteristic function, right, which is going to be the Fourier transform. So there's a lot of new things that we haven't talked about in this lecture series. You may have seen them in other classes before this, but we'll get through it, right? We always do. So let's jump in, because we got a lot of things to cover today. So before we get into the central limit theorem itself, we have to talk about Prohorov's theorem. This is a topic that, well, naturally I probably should have included it in my lectures about convergence of measures, but I didn't. And I didn't think I would actually need it, and then I realized, oh, nope, we definitely need that for the central limit theorem. So we'll just bring it in right here. I'm not going to prove this, I'm just going to kind of state the idea. So Prohorov's theorem is a theorem about compactness in some sense, about convergence. It's very similar to, if you've ever done, well, real analysis and you know about the Bolzano-Weierstrass theorem, which says, oh man, I forgot to write it down. It says, right, that if you have a sequence in a compact set, or a bounded sequence of real values, or in RD, then there should be a convergent subsequence. There should exist a convergent subsequence, or even more like down the rabbit hole, for every subsequence there exists a convergent subsequence. Prohorov's theorem is going to give us something very similar, this idea of sequential, or sometimes called relative compactness, but for sequences of probability measures. And yeah, if you want to know more, I would recommend reading that book, Convergence of Measure by Patrick Billingsley. I think it was called Convergence of Probability and Measure. I forget. The one about convergence by Patrick Billingsley. Anyway, the first thing we need is the definition of uniform tightness. This is in some sense going to be like the boundedness or the compactness condition for our, or let's say a boundedness condition for our sequence of probability measures. So a collection of probability measures mu I from, well, doesn't even really have to be I from 1 to infinity. It's just we have a collection of measures. Doesn't have to strictly be a sequence. We'll just say I in I. In a metric space. We need a metric space, so we have, well, things like, well, a metric and the topology defined by that metric and all the open sets and all of the sets that we need to make this definition make sense. Anyway, a collection of probability measures in a metric space is said to be uniformly tight if, for all epsilon greater than 0, there exists a k epsilon compact set such that mu of k epsilon is going to be greater than 1 minus epsilon. This is for all, or sorry, mu I, and this is for all I. So what does this mean? That means that for my entire collection of probability measures, there exists a big enough but still compact set that contains most of the probability. So for example, I mean, just think about a normal distribution, right? A Gaussian, a bell curve on the real line. I can find a compact interval big enough so that it contains up to 1 minus epsilon, at least 1 minus epsilon of the probability. Basically what it means is that the mu i's can't like run off to infinity, for example, right? If mu I is, let's say, just a Gaussian distribution, we can't have the means run off to infinity, then it wouldn't be uniformly tight. But if the means are bounded and I guess the variances are bounded, then it should be probably uniformly tight. I feel like that should be a theorem. I'm not sure what theorem it is, but it should be a theorem. It probably is, or something very close to that. Anyway, there is a theorem that we need, and that's Prohorov's theorem, the one I keep kind of, pronouncing as best as I can. And the theorem says one version of the theorem. There's a couple different pieces to the theorem. I'm just going to state the stuff that we need. But it's, for a sequence of probability measures. So now we have a sequence, but it's still just a collection. I'm just ordering it. I from 1 to infinity. If the sequence is, I'll just put UT for uniformly tight so I don't have to keep writing that, then it is relatively compact. Sometimes this is written as sequentially compact. There are a lot of different ideas of what compactness means in mathematics. Luckily, when you're working in spaces like Rn, for example, n-dimensional Euclidean space, most of the notions of compactness kind of coincide. Not always the case, but in this case, then the question is, what does sequentially compact mean? It means, i.e., for all sub-sequences mu sub I sub k, there exists a weakly convergent subsequence subsequence mu sub I sub k sub r, which is just, you know, indices all the way down, weakly convergent to mu, and this is for some mu depending on the sequence, the subsequence, I guess. The point is that if I have a different subsequence and a different subsequence, mu might be a different mu. There's just no really good way to like index it because I have way too many crazy things going on here with I sub k sub r. But the point being is that it's a little bit stronger than saying the subsequence converges. It says that for any subsequence that I pick, I can find a weakly convergent subsequence. And then what you're probably thinking to yourself is, why do I care, right? It's like, oh man. Well, in this case, you care because of a very easy to prove proposition, which is going to talk about how the original sequence converges weakly. So this proposition, which is going to be important at the end of this lecture for the central limit theorem, is if mu I from 1 to infinity, and mu are probability measures such that for all subsequences, I'm just going to write for all mu sub I sub k. For all mu sub I sub k subsequences, there exists a mu sub I sub k sub r that weakly converges to mu. And in this case, it's the same mu every time, whereas up here, this is different, possibly different mu's. That's just to make sure this isn't as confusing. The point is that if every subsequence has a subsequence that weakly converges to the exact same thing every time, then mu I weakly converges to mu. Which means that we could show that a sequence of measures mu I weakly converges to mu if we can show that every subsequence is going to converge to mu. You think, like, is that actually easier? Well, we're going to use that later, so we're going to make use of this. Hence why I'm bringing it in. The proof, which I will include because it's basically 2 lines, is assume not. That is, assume that we don't have this weak convergence. Then there exists an f that is continuous and bounded, right? As we talked about, I guess, 2 lectures ago when we talked about convergence, such that the integral of f d mu I does not converge to the integral of f d mu, right? If we don't have weak convergence, then there has to exist at least one continuous bounded function where we don't have this convergence of the integrals. Thus, because this convergence doesn't happen, there exists a subsequent ik such that the integral of f d mu ik minus the integral of f d mu is, there exists an ik such that, I guess, well, for all epsilon greater than 0, I forgot the first bit. For all epsilon greater than 0, there exists a subsequence ik such that that actually doesn't, we don't even need for all epsilon greater than 0. There exists an epsilon greater than 0 and an ik such that this is true. This is for all k. The point being is that if this convergence doesn't happen, then I can find a subsequence such that this guy, the integral with respect to mu ik, has to stay away from the integral of f d mu. So it's kind of like saying, well, okay, if this convergence isn't happening, then I can find points where I don't get close to that. If I get close to it, then I'm converging to it. However, there exists an I sub k sub r such that mu sub I sub k sub r weakly converges to mu. And this is a contradiction. Because what we're saying is for this subsequence, this thing, like basically the integral with respect to mu sub I sub k has to stay away from the integral with respect to mu. But there exists a subsequence where it doesn't stay away, where it does converge. We get a contradiction, and QED, we're done. Whew. So that was just a little bit of like the appetizer. I shoved that into my notes back in the convergence section because it more naturally falls in there. But it is something we're going to need in what's to come. So little 15-minute appetizer for this. Now, to discuss the central limit theorem, right? You've probably seen this before in like a easy, like simple course in like statistics or probability, where we say, okay, something converges to a standard normal distribution. What in the world is a normal distribution, right? Can you define it in a more measure theoretic sense? Because that's what we're about to do. What is a Gaussian measure? Because we don't have to restrict ourselves to just, well, the normal distribution, like the standard normal. So we say that a Borel measure, Borel being that it measures the Borel sets, gamma, on RB, is said to be Gaussian with mean m and variance sigma squared. I said sigma, it's supposed to be sigma squared. If the measure of a half-open interval AB is equal to this crazy thing, which is sigma square root 2 pi integral from A to B of the not the expected value, the exponent, the e to the minus 1 over 2 sigma squared x minus m, the mean, squared d lambda x with respect to Lebesgue measure. Now, if I define this measure on all of the half-open intervals like this, I can extend it to all the Borel sets uniquely, right? So we can think of a Gaussian measure here, could be applied to any Borel set. We define it in this case, and that's why I'm trying to be a little bit more explicit. Rather than writing dx here, I'm going to write d lambda x to indicate that, you know, we could be integrating this over a less pleasant set than an interval, a half-open interval AB. Also, for sigma equal to 0, gamma is equal to delta m, the Dirac measure, which is just a point mass at the point M. We say gamma is degenerate in this case. is a degenerate Gaussian measure. So there we go. We can take the idea of a bell curve and consider it as a measure on all of the Borel sets over the Borel sigma field. We can extend this to RD, which is going to be important because we're going to be doing the central limit theorem in d dimensions. So this is Gaussian measure in RD, and we say gamma on RD and the Borel sets. I'm just going to write B again rather than writing B of R to the D because it's kind of clear from the context what I mean. Borel sets in d-dimensional Euclidean space is Gaussian if for all linear functionals f mapping RD into R, the induced measure, which is gamma of F inverse on RB, the Borel sets on the real line, is Gaussian as per the first definition. This is the fancy way of basically saying, you know, any linear combination is Gaussian. So if we have well, we haven't really talked about a Gaussian random variable, that's the next definition, but what we're really saying here is that if I have a Gaussian random variable, a multivariate Gaussian random variable, then any linear combination of the components is going to be univariate Gaussian. That's sort of how we get jointly Gaussian, right? Because you could have random variables that are individually Gaussian but jointly not Gaussian. In this case, that's not the case, right? We're saying if we have a jointly Gaussian random variable or a Gaussian measure, we can define it this way. Anyway, then what in the world is a Gaussian random variable? RV. So Z is a Gaussian random variable, RV. Actually, why don't I write it like I had it written better in my notes here. So I'll write it out like that, which is, so a random variable Z from some probability space, omega F, I'm using mu this time, mu, to, maybe I should have used P, that doesn't really matter, to R D Borel sets is Gaussian if gamma defined as mu of Z inverse is a Gaussian measure. So simply put, a random variable, a measurable function, is said to be Gaussian if it induces a Gaussian measure on the Borel sets. Cool. So now we know what a Gaussian measure and a Gaussian random variable is in the context of measure theory. Yeah, we're gonna have to define some random stuff just to make sure that we're all on the same page. So for vectors u and v in RD, the inner product, the dot product, u, v angle brackets like this, is just going to be the sum I from 1 to d Probably should stop using I because I'm going to need complex numbers in a second, but we'll use them for right now, just so I don't mess up my indexing. So we have a dot product, right? In our Euclidean inner product. This thing is bilinear, of course, and we also denote the absolute value squared to just be U. This is the the squared Euclidean norm. It's just a little bit more convenient to write it like this so we don't get confused with the LP norms that we were using in a couple lectures ago for LP norms. So, and yeah, we talked about before what independent identically distributed random variables are, right? Did we last time, or did we talk about... No, of course we did, yeah. We talked because we had to do that for the strong law of large numbers. So again, xi, independent and identically distributed, means that, well, they're identically distributed, so they induce the exact same measures. The induced measures all coincide, almost surely. And of course, they're independent for all pairs I not equal to j. So there's lots of different approaches to the central limit theorem, and I actually thought it would be interesting to take some time this summer and go back through some of the other approaches that people have used to proving the central limit theorem. In this context, we're going to take one of the most popular approaches as per the one that shows up in most of the textbooks, which is based on convergence of characteristic functions. And that leads to the question, well, what in the world is a characteristic function? It's a Fourier transform if you like Fourier transforms, but... So we need the characteristic function, and the idea is that a probability measure mu on... Is it on R? Yeah. I guess we'll just do it this way. Before mu was a measure on omega, now I have mu as a measure on RD, so I'm like, I guess it's not the greatest notation, but we'll just assume this is a new section, right? And now mu is just a probability measure on the Borel sets. So the characteristic function i.e. the Fourier transform, is mu tilde. We're going to use the notation mu tilde t. I should say up here, mu tilde is going to map points in RD. Maybe I'll switch to V. So it'll be like a vector in RD, and it's going to map those into the complex numbers. And what it's going to be is defined as the Fourier transform, or up to the scaling, because the Fourier transform always has some kind of crazy, like 1 over 2 pi or 1 over root 2 pi out front. I never remember what it is, and different authors seem to use different normalizing factors. Anyway, we get this. Dot product x and v, and d mu x. So here we're integrating, right, with respect to the measure mu over the, I guess, over the space RD, and we're integrating the function e to the I, where I is the square root of -1, times this, I guess, the inner product between x and v. Now again, in this case, I is no longer an index, and I have to be careful that I don't accidentally reuse it as an index, because I'm probably going to do that, and I apologize preemptively. Oh yes. We can also invert this above thing to get the inverse, I guess, Fourier transform. If mu tilde is integrable, so that this next thing is going to make sense, with respect to Lebesgue measure, lambda, on RD. You can do this in other more general settings, but what we get is that p of x is going to be 1 over 2 pi to the d integral of mu tilde, I used t here, v, I like v better now, of this thing with the minus I x t close bracket d lambda t. And this is equal lambda almost everywhere. So this is the inverse of the Fourier transform, and px is the probability density function. Running into that. For measure mu. So again, we didn't really talk about probability densities, but yeah, it's basically it's this whole thing that the integral of f d mu would be the integral of f times p d lambda, where it's with respect to Lebesgue measure. In some sense, we're taking the derivative, right, of the distribution function, or the Radon-Nikodym derivative with respect to Lebesgue measure, but I'm not going to get into all that because it's not directly relevant, and I mean, it is important, but I'll leave that to your own investigation. The point is we can do a Fourier transform of a measure and we get something called a characteristic function. Now, why is that important? Well, it's important because we're going to use the convergence of the characteristic functions to show convergence of the measures, weak convergence of measure. But we need another definition, so now we're going to talk about the convolution. Right, so what do we have? For two measures, mu and nu on RD Borel sets, the convolution measure, just to indicate that what we're getting out is a measure, is defined as mu star nu, and this is applied to a Borel set B, and the way we measure that Borel set B is we take the integral, this is defined as nu b minus x d mu x. Yes, and this is for all Borel sets, any Borel sets, and where b minus x is the Borel set B but shifted by x. So this is all of the y values in RD such that y plus x is in B. So in some sense, what we're doing, if you look at this integral, is we're taking the set B and we're shifting it all around to every possible place we can in all of RD, d-dimensional Euclidean space, and we're measuring it with respect to nu, and then we're, I guess, integrating over that whole thing with respect to mu. So the convolution has some nice properties to it. I'm not going to prove them, I'm just going to note them. And you can try it yourself if you really want to. Note. The operator star, right, is like addition plus multiplication cross like x. So this operation star is both associative and commutative. I mean, it's not immediately obvious that it should be commutative, but you can try to show that if you want. Also, the characteristic function basically mu star nu tilde, which is terrible notation, but the characteristic function of the convolution is going to be the product of the characteristic functions. And this is kind of like the key reason why you love this thing, because the characteristic function is going to turn a convolution, which is a little bit hard to get your head around, into a product, which is great, because I love multiplying stuff together, right? Also times 2 for independent random variables x and y with measures, corresponding measures, mu and nu, x plus y has induced measure mu star nu. And this is another important thing, that when I add random variables together, I convolve the measures, the distribution functions, or the measures. And that's why this is going to be important, because the central limit theorem, much like the law of large numbers, just means we're going to be adding a bunch of stuff together. But whereas with the law of large numbers, we had everything going to 0 almost surely, in this case, we're not going to 0. We're converging in measures, which means the convolution of the convolution of the convolution, etc., 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 is going to have to converge to something. And having something like mu1 star, mu2 star, mu3 star, mu4, etc. is going to be a headache. But a product of characteristic functions is a lot easier to work with. That's why people like to use this approach to proving the central limit theorem. All right, we need a uniqueness theorem. Uniqueness of, I guess, tilde, for lack of a better way of writing this out. The point is, let mu and nu be probability measures if mu tilde is equal to nu tilde, then mu is equal to nu. So if the characteristic functions coincide, then the measures coincide. How do we show that? Well, we're actually going to use the Gaussian measure to get that. So proof. Let gamma sigma be a mean 0 Gaussian measure, as defined above, on RD with variance, with, I guess, covariance matrix sigma squared times I, where I guess I can say ID, a d-dimensional identity matrix. Maybe I'll write covariance matrix, like that. And then we are going to denote, we're going to write mu with sigma in the exponent to be mu convolved with gamma sigma. So we take our normal Gaussian, or our Gaussian measure, and we convolve it with mu to get mu sigma, and same for nu sigma. We're going to do the same thing there. So it can be shown that Okay. Edit out the sneeze. If I remember. I might forget. It can be shown, which means I'm not going to actually do it, because I'm going to be lazy, that the corresponding density functions, which exist because convolving with a Gaussian measure is going to give us a density, something that's I guess that is like a C infinity, I think, if I recall. But anyway, it can be shown that the corresponding density functions for mu and nu sigma are p sigma of x, which is going to be 1 over 2 pi to the d, both things to the d, integral of mu tilde t, and then this is going to be e to the what? To the minus I. This is the inverse Fourier transform, or the transformation. But we're also going to get the Gaussian bit, which is 1 over, I switched to t. We'll use t. Doesn't really matter. Sigma squared norm, Euclidean norm, t squared. And this is d lambda t. So again, we've got the Fourier, or the characteristic function, the inverse Fourier thing, and the characteristic function for the Gaussian for gamma sigma, which I didn't tell you what that is. But again, if you believe from what I said above that if I convolve mu and gamma, then the characteristic function should multiply, then that's exactly what's happening inside this integral. I'm multiplying two characteristic functions together, and I'm using the e to the minus I inner product tx to basically do this inverse transformation. Anyway, we get the exact same thing in the q case, except, well, I'm just going to say it's the same thing, but we're going to get a new tilde t, and then everything else is exactly the same here. So there's really no difference between the two lines, except that I have these two things. Well, that's pretty cool, because since mu tilde coincides with nu tilde by assumption, then we have that the density function of these two density functions coincide, because mu tilde and nu tilde are exactly the same thing. So p sigma, q sigma, exactly the same thing. And then the measures mu sigma coincide with nu sigma, and this is for all sigma greater than 0. What we want to do is we want to take sigma to 0. Oh, well, there goes my filter. I better not blow too hard into this thing, or we're going to get some nasty... This place is just falling apart. Anyway, what we want to do is we want to take sigma to 0, because what we're saying is I can convolve with any any Gaussian measure with positive variance, and make sure my thing's still recording. Yeah, good. Want to make sure we're still getting audio here. You're going to get the terrible camera audio rather than my nice mic here. Anyway, the point is we want to take sigma to 0 to conclude the theorem. So next is going to be let sigma go to 0. And we want sigma to go to 0, but we're not going to do it just yet. Let's say let x be a random variable corresponding to mu, i.e. the induced measure from x here is going to be this measure mu. And z corresponding to gamma 1. So z is our standard normal random variable, multivariate normal random variable. Then the measure mu sigma comes from x plus sigma times z. Again, you can think of this as we're taking the standard Gaussian z, we're scaling it by sigma, which means the variance is now sigma squared. We're convolving it with x, and we're getting our measure mu sigma. Therefore, x plus sigma z converges almost surely to x as sigma goes to 0. This is pointwise for almost all omega, right? Think of this as x of omega plus sigma, some constant, times z omega. So for any omega, right, as it's going to be fixed, right? It's just going to be some value for x and z. As sigma goes to 0, this second bit, sigma z, goes to 0 almost surely, that is pointwise, and we're left with just x over. Therefore, convergence in probability. Therefore, convergence in distribution, which means that mu sigma is going to converge weakly to mu as sigma goes to 0. And since, well, we have mu sigma converging weakly to mu and nu sigma converging weakly to nu, and this guy and this guy are the exact same sequence, we have that mu is equal to nu. And the limit is unique, right? The limit has to be unique in this case. QED. Was that a... yeah, good. That's it. All right, so that's pretty cool. Now we can state the central limit theorem, state and prove it, and we're done. Well, it's going to take a little bit, but... So here's the main theorem we're interested in today, CLT, the central limit theorem, and it says let omega f mu be a probability space. Yeah, last time I used omega fp, now I'm using omega f mu, but same thing, right? Doesn't really matter. Xn, n from 1 to infinity, are IID random variables, right? Independent, identically distributed random variables on, well, that map from omega into D, RD with Borel sets, such that the expected value of xn is going to be 0 for all n, right? I mean, they're all IID, so of course it's for all n. Mean 0, and the second moment has to be finite. So central limit theorem requires a second moment. It's actually one of the reasons why in statistics you often have, well, people like to estimate stuff in statistics, right? You get what's an estimator? An estimator is what we did last time. Law of large numbers, something converges to a point. When we want to do convergence in distributions, we're doing kind of like second order statistics. We're doing confidence intervals. We're doing hypothesis testing. We need second moments things are actually a lot harder usually when you have to deal with that. That's why most research papers always seem to be proving that something converges to something else, but, well, in a law of large numbers sense, but not necessarily in a central limit-like sense. Anyway, as before, let Sn be the sum J. I don't want to use I because I should be reserved for, I'm going to try really hard not to use I because we need to reserve I for the square root of -1. Anyway, Sn is the sum of the first n xj's. Then the claim is that n, the -1/2 Sn, is going to converge in distribution to Z, where Z is a Gaussian random variable with 0 mean and covariance sigma with covariance matrix sigma, right, with ijth entry sigma ij equal to the expected value of x nj x ij jk. Just kidding, we need jk here, not I. There it is. N doesn't matter, it's IID. All right. Multivariate central limit theorem. Let's see if we can prove it. Well, we're not going to prove it just yet. First, we're going to state a lemma and prove the lemma. And the lemma is going to need Prohorov's theorem, which is precisely why I introduced it at the beginning of this lecture. So, lemma for a uniformly tight sequence of probability measures, let's say mu I on Rd, if for all V for all vectors V in Rd, if mu I V, the characteristic function, so this is basically pointwise convergence of the characteristic function. So if the characteristic functions converge pointwise, that is for all V, then we have weak convergence of measure. Where mu corresponds to mu tilde. So whatever mu tilde is, right, the limit of the characteristic function, the limiting characteristic function is going to be the corresponding characteristic function of the measure mu that the mu i's converge weakly to. That's a terrible sentence, but hopefully the point makes sense. Characteristic functions converge pointwise, then the measures converge weakly. Do you believe it? Let's prove it. Right, so mu I are uniformly tight. Therefore, our good friend Prohorov says that every subsequence mu ik has a convergent subsequence mu ik. I'm using I again, aren't I? All right, that's fine. We'll use I in this one because it's the lemma, and then we'll not use it in the try really, really hard not to use it in the proof of the central limit theorem itself. Anyway, yeah, there's a convergence subsequence. So what does that tell us? Well, all these subsequences have a corresponding sequence of characteristic functions that converge to mu tilde. So the point is that we have all these subsequences. They're all converging. All of them can be transformed into their characteristic functions. All of the characteristic functions are going to converge to the same mu tilde. Thus, yeah, by uniqueness. Thus, by uniqueness from above, that uniqueness theorem that we proved, all mu sub I sub k sub r weakly converge to mu. But that proposition that we proved at the very beginning by the prop from above, the proposition from above, we know that if all the subsequences, all the subsequences weakly converge to mu, then the original sequence has to converge weakly to mu. Cool, QED, we got our lemma. Yeah, we're going to use this, right, to basically show that if the characteristic functions converge in the central limit theorem, then the measures will converge. So we need the characteristic functions to converge to the characteristic function of a Gaussian measure. Got to get all those words right. All right, we're back with the proof of the central limit theorem. I also got my filter back so I can say proof and hopefully not blow out your headphones, right, with that white noise sound. Anyway, yeah, so let's prove the central limit theorem. So random variables xj are mean 0 and independent. Therefore, right, the expected value of the inner product xj xk is going to be 0. This is for j not equal to k. Right, so this is just in some sense saying that they're uncorrelated, right? Independence implies uncorrelated, but of course if they're independent, mean 0, that means we're going to get this inner product is just going to be a big sum of xj somethings times xk somethings. Independence means I can take the expected value of each of these separately, the mean 0, the whole thing 0. Cool. Thus, the expected value of n to the -1/2 of our sum, Sn, the sum of the first n terms squared. So this is, again, this absolute value squared. Remember, these are vectors now, random vectors. So we have to think about this as in a Euclidean norm, the squared Euclidean norm. So what this is going to be, right, is, oh, that is completely wrong. What this is going to be is 1 over n, the expected value of the sum, and this is going to be j, k from 1 to n, x, j, x, k. And this is precisely just going to be, well, it's the expected value of, well, it's the expected value of xj squared in Euclidean, a squared Euclidean norm, summed up n times, but divided by n. And of course, the expected value is the same for all j, so it doesn't really matter at the end which j we use. So now that we have that, for any epsilon greater than 0, there exists an m epsilon greater than 0, such that the expected value of this Euclidean norm squared of xj divided by m epsilon is less than epsilon. Do we believe that? Well, yeah, of course, because this thing has finite. By assumption, right, in the central limit theorem, this expected value of the Euclidean norm of xn squared is finite. If it's a finite value, then I can find an m big enough so that when I divide by that m, I get something that's less than epsilon here. Thus, by our favorite Russian, I think Russian, mathematician Chebyshev. It sure does sound Russian, though who knows where Chebyshev was hanging out. By Chebyshev's inequality, we have that the probability I guess I should technically use mu, right? Oh no, I guess if we think of this as a probability space, yeah, no, that doesn't make sense. If we think of this as like a probability space, right? I guess I didn't define it the right way. See, always got to start off with the, right, omega f p, a prob space, and the xj's are mapping from omega into r d. So in this case, if we're mapping back, then we can talk about the probability that this guy is greater than m epsilon. And Chebyshev tells us that this has to be less than epsilon. Well, it's less than, right? If we use this line, if we use this line here, it's going to be less than the second moment of the xj divided by m squared. Or actually, this is supposed to be m squared, isn't it? Let me double check that. Yeah. There's supposed to be, I'm going to put it in red just to indicate there's a square right here. It's supposed to be m squared, so that this whole thing becomes less than epsilon when you apply Chebyshev. So why do we do that? Well, what does this mean? This means that the sequence n minus 1/2 Sn is uniformly tight, because I can find an m large enough. So for any epsilon greater than 0, I can find an m large enough such that the probability of being greater than m outside of the interval plus m to minus m is less than epsilon. And that's the interval plus m to minus m is a compact set, right? A compact interval. And thus we have uniform tightness for our sequence. So that's good, because we just had some theorems about uniform tightness that we're going to want to use. Specifically, the one that says that if a uniformly tight sequence of probability measures has convergent characteristic functions, then the measures converge weakly. And that's exactly what we have. Now we have random variables. They induce measures. These things are uniformly tight, so all we have to do now is show that the characteristic functions converge to conclude the central limit theorem. Can we do it? Well, for a vector v in Rd, right, random variables, we can consider these random variables where I take V and I do an inner product with xj, and these are IID real random variables, right? And sometimes I'm using a linear functional to project xj onto into a random variable on the real line. But anyway, yeah, with the expected value by linearity, by by space linearity, not bi linearity, by the linearity of this, I guess by the bilinearity of this, we get 0 mean. And furthermore, we know that the expected value of the second moment, or the second moment, the expected value of this thing squared, is going to be finite. Cool. So now what we have is we have a sequence of IID real random variables with mean 0 and finite variance. And this can be done for any choice of V, any linear functional, right? So now we're going to say let h of V be defined as the expected value. Well, it's the characteristic function, right? It's the expected value of the exponential of I square root minus 1 V xj. So then the question is, well, what is that thing? Well, I don't know. But we can find out an approximation for it using Taylor's theorem. So don't know what that is, but I know that if I plug in a 0 here, I'm going to get the expected value of e to the 0. The expected value of 1 is just 1. If I take a first derivative, a gradient of this thing, well, what am I going to get and evaluate it at 0? What I'm going to get is a big vector of, I guess, I times x, the vector xj. But that's mean 0. Xj is mean 0, so this thing is just 0. When we do our second gradient, well, now what we end up with is the expected value. There's going to be 2 i's coming out, so we're going to get something like minus. The minus here is coming from the fact that we have an I squared, which is equal to minus 1. And then we're going to get the expected value of like an outer product. So if we think of xj as a vector, as a column vector, we can write this as xj, wait, which way are we going? xj transpose, outer product. This is the covariance matrix that we started with from the beginning. Covariance matrix. What comes after that? Don't care, because I only really care about the first 2 derivatives, because that allows us to do Taylor's theorem. So by Taylor's theorem, what do we get? Well, we get that I don't know what h is, but I know how to get approximately what h is, which is h is going to be h0 minus, well, the first derivative, the gradient there is 0. The second one is going to be 1/2 from 1 over 2 factorial, right? And then it's going to be v transpose, it's going to be a quadratic form, v transpose v. And lastly, we're going to get something that's going to be little o of absolute v squared. This is the Euclidean norm. I think I used the double bar in my notes, but I'll change that later. This is Euclidean norm squared. Okay, cool. So Taylor's theorem tells us that this thing that we're computing here is going to look something like that. Well, what does that mean, right? Well, therefore, for any fixed, I'm supposed to take a log. I think I'm supposed to take a log. Let's just write this out, and then I'll double check. For any fixed v, right? The expected value. Oh no, I'm not taking a log. I'm not taking a log. I'm taking this to the nth power. Okay, I feel better. I feel better. I thought like I was missing a logarithm somewhere. The logarithm doesn't need, it's coming up here. So for any fixed vector v in Rd, what we have is that the expected value of the exponential of exponent I inner product n to the -1/2 Sn comma v, fixed v. Well, this thing, again, exponents, right, are, if I add up a bunch of exponents, I'm just multiplying these things together. So what this is equal to is this is equal to my h function, n -1/2 v to the nth power. Okay, so I'm multiplying this h function times itself n times, and I get a v, but v is being scaled by the square root of n. Well, if I use my Taylor's theorem definition up here, then this thing becomes 1 minus v transpose sigma v quadratic form divided by 2n, because I have a square root n that gets squared in the denominator, because each v comes with a square root n. And then I get a little o term, v squared divided by n, and this whole thing to the nth power. I'm not sure if I told you what little o is. Right, little o just means that it's like a remainder term in Taylor's theorem. It means that this term is going to go to 0 faster than v, I guess the v squared. So basically the point is that little o of v squared here divided by v squared is going to go to 0 as v, I guess, squared goes to 0. So the point is that the numerator, the little o thing, is going to 0 faster than v squared is. So it's going to 0 at a faster than, I guess, like quadratic rate you could think of. The point being is it's negligible. We don't care about it because in the limit, as n goes to infinity, well, what do we get? This guy is basically going to vanish. And what we're left with is something that looks like 1 minus something divided by n to the nth power. Well, in the limit, that's an exponential function. That's just e to the this thing, which is minus 1/2 v transpose sigma v. Cool. So what did we do? Well, this is the characteristic function for z from the beginning, which was our multivariate Gaussian mean zero random variable with variance, covariance, sigma, matrix sigma. Thus, by the above lemma, what do we have? We have that n minus 1/2 Sn converges in distribution, weak convergence of measure, to z. standard, or not standard, just a Gaussian with a specific covariance matrix. QED, we're done. Look at that. That was record time for one of these probability and measure lectures. Cool. So that's the whole central limit theorem. Like I said at the beginning, there are different ways that you can go about trying to prove this result. The one based on characteristic functions is perhaps one of the most common ones you'll see. Maybe in a future lecture when I have more time to just make lectures on random stuff, we can try and show different ways of proving the central limit theorem, because they all offer kind of different bits of intuition that are really interesting to consider. In this case, it's all about convergence of the characteristic function, and it really relies on Taylor's theorem. I mean, what we're basically saying is use Taylor's theorem, use convergence of characteristic functions, and the fact that characteristic functions start to multiply when you add random variables. So that's all good stuff. There is another slightly more general version of the central limit theorem that I thought about presenting. I'm not going to do it in this lecture, and I'm not going to do it in the next lecture because this is only for a 13-week course, and I want to do the ergodic theorem in the next lecture. But there is, I think it's a Lindbergh or Lindenberg, I can't remember the guy's name. The person, Lindbergh, has a central limit theorem where the distribution, where the x's do not necessarily have to be identically distributed. So there are ways, I guess that's what I'm trying to get at in my summary here, is that there are ways to relax the central limit theorem. You can get a central limit theorem where the xn's are not necessarily IID. They're still independent, but they may not be identically distributed. As long as the variances are kind of nice enough, you can get another type of central limit theorem. You can do the central limit theorem. I'm pretty sure there's a martingale central limit theorem, which would be for not having some type of dependence in your data, but I'd have to double check that result as well. The point is, it doesn't just stop here, right? This is, the central limit theorem, but there's lots more central limit theorems out there that you can extend this to. So hopefully you go out, explore, find more central limit theorems, enjoy the fact that you're normal, I'm normal, we're all normal, right? Because that's what the central limit theorem kind of says, right? Bell curve, we're all in that bell curve together. With that, I will end this lecture, and in the last one for this sequence of 13 lectures, we'll be doing the ergodic theorem. It's a really cool result. It's kind of like strong law of large numbers on steroids, because it's strong law of large numbers, but so much more than that, and we can use it to prove the strong law of large numbers. So in some sense, I didn't even have to do the previous lecture. I could have just done the next one on the ergodic theorem, but it's nice to see all of these, isn't it? So hopefully you'll stick with me for one more lecture, and I'll see you in that one. Stay tuned for more.